Hello students, welcome to the lecture series of differentiability of functions, and this is our lecture number 1. And in this lecture we are going to discuss the theory part of the chapter. So please try to understand the theory part because this is the basics of the whole differentiation. Therefore you should concentrate to the class for future references. So let us go through the video. So first of all, we are going to write the definition of the differentiation, and this is already discussed in your first year classes. And so just we write the definition, and how this definition is obtained we will not discuss here because we already know how to obtain the differentiation of a function. So see the definition first. So let y is equal to fx. This is a function, real valued function taken, and then we have to find the differentiation of this function with the help of the first principle of derivative, and that is already known to you. You just see the first principle of derivative. What was the first principle of derivative? You see that one. So that is dy dx is equal to, it is denoted by f dash x. We discussed in the first year in details about this, and that is equal to limit h tends to 0 and the function fx. So we should take a small increment in the value of x, that is f of x plus h, then minus fx divided by h. So this is our first principle of derivative. With the help of this theorem or this formula, you can find the derivative of a function. So but here in this chapter we should discuss about the differentiability of function at some particular point. It is not defined at some particular point. It is differentiation, and it is first principle of derivative, and it will give the differentiation of entire function in all points of the domain of the given function, whatever be the function is given. Okay, so this definition will give us the derivative of the entire function at each and every point of the domain of the function. But in this topic we should discuss the differentiation of function at some particular point. The point will be given in your question. Okay, so here in definition we should consider a point, some x is equal to a only. You see here differentiability at a point. So first of all we take y is equal to fx. This is a real valued function, and x is equal to a. This is a point in the domain of the function, and you already know what is domain of a function. So this point is taken from the domain, but in case of question this point will be given. X is equal to some 1 or 2 or 3, say half. That types of point will be given in case of questions, but here we are writing the definition. Therefore we take a simple point from the domain of the function. Okay, then the left hand derivative will come from here, but differentiability means we have some particular definition at some point. When we discuss the differentiability of function at some point, then it is necessary to find the left hand derivative and to find the right hand derivative. If that two derivatives are equal, values of the two derivatives, left hand derivative and the right hand derivative, these two derivatives are equal, then we say that the function is differentiable. Okay, we will discuss here is the left hand derivative. For derivative we are to use this definition, but at x is equal to a, therefore x should be replaced by that particular value of x, a. It should be taken as a because we are taking a point in the domain of the function as x is equal to a. So here we should write x is equal to a. Derivative will be obtained from here. Point is a, so we replace x by a, and this time it is left hand derivative. So this h tends to not only 0, h tends to 0 minus this time, because we are going to find the left hand derivative. So nothing complexity here, you just see. Then left hand derivative, it is left hand derivative. Symbolically we write L f dash a, and since it is left hand, so we write h tends to 0 minus here. This x equal to a because the differentiation is obtaining at the point a, so it is a plus h. This x is a, fa divided by h, and this limit can be converted to this one also by taking a simple substitution. You see the substitution first. Okay, so you see the substitution is taken as a plus h, this is taken as x. You see, compare this to this, a plus h is taken as x. So h will be what? H will be x minus a. So this is x minus a. Fa is fa, remaining same. And what is x tends to? Because this time h is converting to x, therefore the standing limit should also be sensed. So you see here, when h is going to 0, then x will go to a. So we write x is going to a minus because of left hand limit. Okay, so this is our definition of left hand derivative of the function. Then the right hand derivative. The right hand derivative is nothing but RHD. This is right hand derivative. So it is r f dash a, and that will be equal to, since this time it is right hand, so h tends to 0 plus. Now definition of derivative is remaining same here, a plus h. A is because point is x is equal to a here, so it is a plus h minus fa divided by h. You got my point. And same substitution will be here again. A plus h is taken as x, so fx minus fa divided by h will be then x minus a, and it is a plus because of right hand limit. Okay, so a right hand derivative, and this is left hand derivative. So this function y is equal to fx function will be differentiable at x is equal to a point. It will be differentiable at x is equal to a point if these two limits are exist finitely and equal. So we write that one. So if LHD mean left handed derivative and RHD mean right handed derivative, if these two are equal, mean the limit, that particular limit is exist, that is LF dash a equal RF dash a. You may use this or you may write this also, both symbol are acceptable. Then the function y is equal to fx is said to be differentiable or derivable. At what point? At x is equal to a point. So this is very comfortable. It is generally written to represent the differentiability of function. So therefore, if the limits, what are the limits? This limit h tends to 0, f of a plus h minus fa divided by h, this or this one. If these two limits exist finitely, this limit exists finitely. When limit exists finitely? When the left hand limit and the right hand limits are equal. We know from the limit of the limit of function from the previous chapter actually. So when a limit is exist, if the left hand limit and the right hand limits are equal, then we say that the limit exists. So this particular limit exists. This particular limit is nothing but derivative. So this time this limit is known as derivative of function at x is equal to a. So this particular limit, this or this, by taking a plus h is equal to x only here. So we should generally use this, not this. Okay, so if this limit exists finitely, then we say that the function y is equal to fx is differentiable or derivable at x is equal to a. And in that case we should write like this, dy dx at x is equal to a. This is the denotation of a function, differentiability of function at some particular point. We should write x is equal to a is equal to, this is the definition. This time you should not write h tends to 0 plus or 0 minus or x tends to a plus or a minus, because this is full differentiation, mean here actually both the limits are equal and same, equal and exist finite. So therefore need not to write the x tends to a plus or x tends to a minus. Both the limits are given here. So the differentiability or differentiation of function at some particular point is denoted by this one. You should know that this line. So this is the differentiation. If this limit exists mean left hand and right hand are equal and finite. So then we say that the function is differentiable at the point x is equal to a. So then we write differentiability at in an interval. It is derivative in an interval. Interval means it may be a closed interval, it may be an open interval. So in the previous topic we discussed the differentiability at a point, but this time in an interval, because an interval contains infinite number of points actually. So how to define that types of differentiation? You see here, let y is equal to fx be a real function, and then it is said to be differentiable or derivable in the open interval. This is open interval ab, mean this a and b is excluded from the discussion. You are to consider the points, those points which are between a and b, excluding a and b. So in that interval the function is said to be differentiable if the function is differentiable at every point in this interval. If this interval say 2 up to 4, if this interval I am writing here, you see, if this interval is say the open interval 2 up to say 5, open interval, so you should exclude 2 and 5. So this is the real line, say this is the point 2, this is the point say 5. Then in this interval the function is said to be differentiable if it is differentiable at every point of this interval. Every point means this all points, every point of this interval. If it is differentiable, then we say that the function is differentiable in the interval. Open interval means you should exclude this point 2 and you should exclude this point 5. You should just consider the inner points of this interval, these points. Okay. So then you see, and differentiable, how to check differentiable, you already know by using that definition, limit h tends to 0, that one. Okay, again the same function is said to be differentiable in the closed interval. So when we take the closed interval, then this time a and b are included in the discussion. So this function is differentiable in the closed interval if it is differentiable in open interval, mean between a and b the function should be differentiable at all points between a and b, as well it should also be differentiable at the end points a and b. So at the end points a and b, you see here, so if your point a is here and if your point b is here, and this time closed interval, so first it should be differentiable in the open interval, mean all points between these 2 points, and it should also be differentiable in the at the point x is equal to a from the right side. This is from the right side because left of a is not defined, this side is not defined, and this side is also not defined. It is defined at a and b because a and b are included here. So at the point a, right hand derivative should be exist, and at the point b left hand derivative should be exist. This is RHD here should be taken for x is equal to a RHD and x is equal to b LHD. At that 2 points the function should be differentiable, as well at all points between a and b it should be differentiable. Okay, so if this condition is satisfied, then we say that the function is differentiable in the closed interval ab. I think it is clear to you. So then it will be better if you solve some problems about this topic, then it will be more clear to you. So I have written here, you see, x is equal to a and in the interval ab, if it is differentiable at the point, at each point, mean every point of this open interval ab, differentiable from right at x is equal to a and differentiable from left at x is equal to b. At the point a you should check the right derivative, at the point b you should take the left derivative, and in between a and b at all points. Is that clear? Okay, so I think it is better understandable to you. Then we write that an important theorem, it is very important theorem actually, and frequently this theorem is asked in your exam. Okay, so you should understand the theorem conceptually. Okay, so first we write the theorem only. The theorem is, if a function, whatever be the function, that is no matter. So if a function is differentiable at a point, you have given a function and it is differentiable at some point, then it is necessarily continuous at that point. Mean, if a function is differentiable, then it must be continuous at that point. Very important. If a function is differentiable at a point, then it is continuous at that point. But the converse of this theorem, converse means if it is continuous, then it may not be differentiable. That is reverse case. So we have also written here, but the converse is not true. What is the converse? Converse is, if a function is continuous, then it may not be differentiable. It may not be differentiable. So that is the function, that is, if a function is continuous, it may not be differentiable at that point. Okay, so both part is important. This part is also frequently asked in your exam. This part also asked in your exam. So you should understand the theorem and proof. So we go to the proof of the theorem. So first we will prove this one. We should have a differentiable function, and we are to prove that that function is also continuous at that point. The point is any value of x. So we take that one. The proof part, let the function be y is equal to fx and x is equal to a be that point. So we are taking here this function y is equal to fx is differentiable at x is equal to a. It is given, and since it is differentiable, and by the definition of differentiable we just discussed, we have a definite limit. And what is the limit? F dash a is equal to limit x tends to a fx minus fa divided by x minus a. You know that one. This one. This limit exists finitely, mean this f dash a has a definite value, 5, 6, 7, 2, 4, half, minus 3, minus 4. That's like point will be f dash a. So exists finitely. This limit exists finitely mean the function is differentiable. Exists finitely mean this left and the right of this limit are equal actually and finite. Okay, so now we are to prove that this function is continuous, because the theorem is, if a function is differentiable, then it will be continuous. So we are taking a differentiable function, and our task to find that it is also continuous. And what was the theory for continuity of a function? The continuity of a function already discussed in the previous classes. Continuity of a function means the limit value of the function is equal to the function value of the function. You already know that one. If the limit value of a function is equal to the function value of a function, then we say that the function is a continuous function. And so we are to prove that one. Actually we are to prove what? We are to prove this. You see here, you have to prove this limit x tends to a fx, this is your limit value, should be equal to fa, this is your function value. Just we are to prove this one. Okay, so I am erasing this one. You see here. Now limit x tends to a fx, we are to just find the limit of this function, and here it is remaining same. I am taking two extra terms here, minus fa plus fa. So this will eliminate each other, so it is actually equal to this. Then you see we have simple technique here. Limit x tends to a. X tends to a mean we already know it is not exactly equal to a. X tends to a mean x is not exactly equal to a. You see here, I am writing this one. X is not exactly equal to a. So what is the conclusion? The conclusion is x minus a, this is not 0. This is your conclusion. Since x minus a is a non-zero number, therefore we can divide this entire part fx minus fa, this term, by x minus a, because fx minus fa by x minus a, because x minus a is a non-zero term, and that is why this x minus a is extra term taking here, x minus a is taking here, so this and this will cancelled out, fx minus fa will be remain same. So obviously we can write like this. Then this limit will act on this part as well as this part, because we have a theorem for limit of fx into gx, then limit fx into limit gx. So by that theory, this limit will act on this and as well as act on this one also, you see. So this part is actually what? This is f dash a, it is a finite value, 2, 3, 4, 5 like that values, finite value. And if you use that limit here, a minus a will be there, so it is 0. And fa is remaining same, this is a constant term, so node limit value will be there for fa, it is a constant number, so fa, so this is 0 plus fa is equal to fa only. So ultimately we what we have obtained here, we obtained that this limit value is equal to the function value, and this is the condition for a function is continuous. So we are taking here fx as a differentiable function at some point x is equal to a, and we obtained here that it is always continuous at that point. So this is the forward part of the function, and now we are to prove the backward part. Backward part mean converse part. Converse part mean this time we should take a continuous function, and we are to prove that that continuous function may not be differentiable function. May be differentiable but may not be differentiable, it is not sure. In this case, the forward part tells us if it is continuous then it must be if it is differentiable then it must be continuous. The forward part of the theorem tells us that if a function is differentiable then it must be continuous. But the reverse part mean the converse part, if a function is continuous then it may not be differentiable, may be differentiable but may not be differentiable. That is why the converse part is not true. And to prove that part, we have to take one counter example actually, because whenever we are to prove some negation mean not, then it is very easy to check, or it is very easy to prove by the help of a counter example. So you see here, therefore fx is therefore the function fx is continuous at x is equal to a. Okay, so this is your first part. Then go to the converse part. The converse part, this time we should take a continuous function at some point, and very familiar continuous function is the modulus function. You already proved that fx is equal to mod x in the previous chapter. Fx is equal to modulus x, it is a continuous function at the point x is equal to 0, you already know. So we should take the help of that example. So to prove that the converse of the above theorem is not true, let us consider the function fx is equal to mod x. You may take some other function which is continuous but not differentiable. So this is very familiar, so I think you should take this one. So now at the point x is equal to 0, we just check or we prove this is a continuous function. We already know, because at x is equal to 0, fx is equal to modulus x, this is a continuous function. We proved this theorem, this one, in the previous chapter. So left hand limit x tends to 0 minus fx, 0 minus because we are checking the continuity at x is equal to 0, so 0 minus fx, it is modulus x, and converting h tends to 0, so it is 0 minus h, will be mod minus h is equal to h only, so 0. Similarly the right hand limit is also 0. Similarly f0 is modulus of 0 is also 0. So left limit is 0, right limit is 0, and f0 is also 0. So all these three are equal, so therefore LHL equal to RHL is equal to f0, thus the function is continuous at x is equal to 0. Also, you may also remove the modulus sign to check the continuity of this function. You may also remove this modulus sign, then check continuity. That will also be okay. This is another method to check this modulus function is a continuous function. So left hand limit, right hand limit and function value are equal. So the function is continuous at x is equal to 0. So now we prove this function is not a differentiable at that same point x is equal to 0. So to check the differentiability of a function, we just use the definition of the differentiability. So definition of differentiability you already know, limit x tends to a, second form. You should use the second form, that is very easy than the first form. So x tends to a minus left hand limit and x tends to a plus right hand limit, and the limit is fx minus fa divided by x minus a particular limit, then it will define the differentiation. Okay, so L f dash, the point is 0, so L f dash 0. This definition will remain same. This time a is 0 here, you see a is 0. Then fx is modulus x, f0 is already here, f0 is 0, this is x minus 0. X is converting to h, so it is 0 minus h, this is 0 minus h. So mod of minus s is h divided by 0 minus s is minus s, cancelling it will be minus 1. Similarly r f dash 0, this is fx, same, it is same. You can understand this one. So 0 plus s is again h, this time by cancelling it is 1 only. So the left hand limit and the right hand limit, this limit, particular limit, mean left hand derivative and the right hand derivative are unequal. So function is not differentiable. But here you see the function is continuous by this one. Function is continuous. Though the function is continuous, we see here that the function is not differentiable, and hence the proof. The proof is, if a function continuous, it may not be differentiable, and we have seen here that it is a continuous function, but it is not a differentiable function. There are so many examples. We will do some problems here also. Okay, so you just write, hence L f dash 0 is not equal to R f dash 0, hence the function is not differentiable at x is equal to 0. So that is the proof of the converse part. Okay, in your exam the question may ask like this: prove that if a function is continuous at some point, it is differentiable at that point. Sorry. It may be asked like this: if a function is differentiable at a point, then it is continuous at that point. Give an example to show that the converse of the theorem is not true. The question may be asked in your exam like this sentences. Okay, so next slide is here. Oh, sorry, this is your graph of the function. Already you know from the previous chapter. This is the point 0, and modulus function is of the shape v, you know already, and 0 point it is continuous, but it is not differentiable. And there is a small technique for you. By observing the graph of a function, you can say whether that function is differentiable or not, by just observing the graph. So if the graph of a function have some sharp point mean it is like this, sharp turn, like this, sharp turn. Like, you just think about this one, my hand, this type of sharp turn. If like sharp turn is there, then at that point where the sharp point is exists, at that point it is not differentiable. It may be continuous, but it can never be differentiable at the sharp points of the graph, and here the sharp point is indicating at the point 0, you see. Okay, so by just observing the graph of any function, you can say whether that function is differentiable or not at some particular points. Just you see the graph of the function has sharp turn or not. If a sharp turn is present, then just vertically below of the sharp point on the x-axis is the point of not differentiability. Okay, so here it is point is on the graph on the x-axis, so therefore the sharp point is at the point 0, so it is not differentiable. Okay, it may be continuous. So the next one, we take some examples here, problems actually. This is your problem. Prove that fx is equal to modulus of x minus 1 is not differentiable at x is equal to 1. Similar question, fx is equal to mod x and fx is equal to mod x minus 1. No difference is there. X is replaced by x minus 1 only, and that was mod x, so the point was x equal 0. This time it is mod x minus 1, so the point will be x equal 1. This one, just you consider here, you see here, so just you consider this x minus 1 as equal to 0, then it will imply x is equal to what? It will imply x is equal to 1. So the point is therefore taken as 1. Okay. So this function is not differentiable at x is equal to 1. It is continuous at x is equal to 1. It is continuous at x is equal to 1 but not differentiable. You may prove that part also. Okay. So just we prove the differentiability part here. So we have the function is fx is equal to mod of x minus 1 and the point is x is equal to 1. So just find L(f)(1) and R(f)(1). So L(f)(1) limit x tends to 1 minus left hand limit, so 1 minus function is f. L(f)(1) is 1 minus, and then fx minus f1, this is definition, fx minus f1 point is 1 by x minus 1. Then x tends to 1 minus fx. What is fx? Fx is mod x minus 1 is there. F1 mean here you take 1, so it is 1 minus 1 will be 0. So I am writing directly here 0 divided by x minus 1 is remaining same. Then make it h tends to 0. So h tends to 0 here. So x is 1 minus h, then minus 1, minus 0 is not written here. This is 1 minus h minus 1, 1 cancel, mod of minus h is h divided by 1 cancel is minus h. So limit of minus 1 is equal to minus 1. Similarly find the right hand limit. R(f)(1) is equal to x tends to 1 plus this time fx minus f1 divided by x minus 1. These are remaining same as done earlier. H tends to 0. This is x replaced by 1 plus h now, 1 plus h, minus 1 is there, f1 is 0, and this is 1 plus h minus 1, 1 cancel, mod h is h, this 1 cancel will be h, so 1 will be there, so right hand limit is 1. So left hand derivative, this is minus 1, right hand derivative, this is 1. So they are not equal, mean the function is not differentiable. So therefore L(f)(1) is not equal R(f)(1), hence the function is not differentiable at x is equal to 1. Okay, so hence the function is not differentiable at x is equal to 1, and this completes the solution of the problem. And this is your graph. This time the point is x is equal to 1, so at the point 1 we have a sharp turn. Okay, so this is your function fx is equal to x minus mod of x minus 1. Okay, so this is our next problem. Prove that the greatest integer function fx is equal to this one in the interval 0 up to 3 is not differentiable at 1 and at 2. These 2 points are included in this interval 1 and 2. So here also for the point 1, find left hand derivative, find right hand derivative, and then you see that 2 derivatives are actually not equal. So simple, function is fx equal to greatest integer x. This is the range of definition. X is equal to 1. Left hand derivative L(f)(1) is equal to limit x tends to 1 minus, because the point is 1, fx minus f1 by x minus 1. Fx is this one, writing here, f1 is greatest integer of 1 divided by x minus 1 is remaining same, making it h tends to 0. It is 1 minus h, this greatest integer of 1, because it is one integer number, therefore it is remaining same. And here it is 1 minus h, then minus 1, 1 cancel. But you observe here, greatest integer of 1 minus h discussed in the previous chapter, that greatest integer of 1 minus h and h is a very small number, 0.00001 type number, say. So 1 minus 0.00001 type number, then it is actually 0.99999 type, and greatest integer of 0.99999 type is simply equal to 0. You know that one. You should take the integer part, so it is 0. This greatest integer of 1 minus h is 0 only, then minus 1 divided by minus h. So we have 1 by h, and this limit can never be defined, because h, there is no possibility to cancel the term h. So this is undefined, so it is not necessary to find the right hand limit. Right hand limit is not necessary this time, because already the left hand limit is undefined. So therefore the function is not differentiable at x is equal to 1. In the similar way, to find the differentiability at x equal to 2 also, So again for x is equal to 2, similarly this time it is L f dash 2 now, L f dash 2. So 2 minus fx minus f2 divided by x minus 2, this function. Similar, greatest integer of 2 will be 2, but h tends to 0 করার লগে লগে তোমার ইয়াটা হয়ে যাব 2 minus h, this time 2 minus h, this is 2 minus h, this positive negative 2 is cancelled, and here 2 minus h mean what? 2 minus 0.00001, like, so it is 1.99999. So greatest integer of 1.999, it is nothing but 1 only, so it is 1 minus 2 divided by minus h. So negative cancel, it is minus 1 by minus h, so simply 1 by h, and again this limit cannot be defined, so you write that one. This is undefined, so it is not necessary to find the right hand limit or right hand derivative, therefore it is not differentiable at x is equal to 2 again. Okay, so this completes the solution of the problem. Now we take this question, show that the function, this one is the function, this is differentiable function at x is equal to 0. That is your first question. The second question is this function continuous at that point? The point is 0 here. So first check the differentiability like this. For x is equal to 0, left hand derivative, first L f dash 0. So L f dash 0, limit x tends to 0 minus, this is the definition of differentiation, fx minus f0 divided by x minus 0, fx, x tends to 0 minus mean x is less than 0, so here x is less than 0, so fx is x square, we write x square. F0 equal 0 is in this line, so if x is equal to 0, it is f0 equal to 0, so 0 divided by x minus 0 is x, one of the x is cancelled, so limit x tends to 0 minus, it is x only, h tends to 0 making, then it is x is equal to 0 minus h here, and putting h0 we get the value is 0. This is your left hand derivative. Then right hand derivative is as similar of this one, rf dash 0, x tends to 0 plus definition, then x tends to 0 plus, this will be plus, you see, this will be plus, this will be plus, so 0 plus means greater than 0, and here is the line greater than 0, so fx is x, f0 is already 0 divided by x, cancelling this, it is 1, and the limiting value is also equal to 1. This is plus, you correct it, this is plus, so it is equal to 1, and we see here these two are unequal, and therefore the limits are so therefore the function is not differentiable. So L f dash 0 is unequal to R f dash 0, so the function is not differentiable at x is equal to 0. And the second question, is the function continuous at that point? Again check the continuity by using the theory of the previous chapter, left hand limit and right hand limit, just find that two. So now left hand limit, x tends to 0 minus fx, 0 minus is this one, fx is x square, h tends to 0 mean x is replaced by 0 minus h, it is square, using h0 it is 0. Right hand limit, x tends to 0 plus fx, x tends to 0 plus mean greater than 0, it is x only, 0 plus, so it is x tends to 0 plus, it is h tends to 0, then x is equal to 0 plus h, 0 plus h, using h0 it is also 0, and f0 is already 0 in here, you see here f0 equal 0 is in this line, so f0 is equal to 0, thus left hand limit, right hand limit and function value all are equal, so function is continuous, so it is not differentiable but continuous. Okay, so this completes the solution of the problem. So you may see the graph of this function also. This is your graph, and at this point you see the function is continuous, this is continuous, but here we have a sharp turn, it is smoothly turned like this, and here from here it is sharp turned, so at the point 0 it is not differentiable but it is continuous. This is your function. So we complete the class here today, and we have one video for this chapter, and after that we will discuss a new chapter. So till then, thank you very much.